So in this section, we're going to talk about bifurcation in two-dimensional system. So it turns out some of the behavior is rather similar to one-dimension problem. We also have saddle node. Think about what that means. That means the creation or destroying of equilibrium. We also have the transcritical bifurcation. So that means what? The stability exchanged. Pitchfork bifurcation. So that's the creation of extra equilibriums. Pitchfork bifurcation in two-dimensional system. So once again, I will give you some prototype problem so that illustrates the different scenarios of what happened to the equilibriums. First example, and then I'll let you guys to think about what type of bifurcation this is. So that's obviously a system where we have a mu as the only parameter here. So what we're going to do here is we're going to use the phase plane. Okay, we're going to use the phase plane. Obviously, when mu is 0, we only have y equilibrium, that's 0, 0. When mu is positive, there will be 2. When mu is negative, once again, there will be none. All right? So think about this, okay? Think about this. So here are different phase plane, okay? You can try to recreate this by yourself. We have the x-axis, all right, x-axis. When mu is positive, the y value, okay, the equilibrium for the y value is always the y value for equilibrium is always 0. Mu is positive. We have positive square root of mu, and we have negative square root of mu. So here there will be the y-axis that I didn't plot here. Okay, I'm going to just plot the phase portrait. Phase portrait. So here's how the phase portrait look like. We're talking about phase portrait here. Okay, so you have to study the sign of x prime and y prime in different region. Okay, in different region. And I take this guy for example. Okay, over here, in this region here, x prime being mu minus x squared. So you think about this. Okay, in this region here, x is bigger than square root of mu. So this guy will be negative. Y prime, which is negative y. But notice in this region here, y is positive. So y prime will be negative. So that's why the slope field will point in downward and eventually converge to this equilibrium. Over here, x prime, it is still negative, but y prime, which is being negative y, it is y down here is negative. Okay, negative y will be positive, so it's moving upward. So you have to do this to different regions here. Eventually, you can create a slope field like this. So this takes a lot more work than what I showed here. The phase portrait eventually will show you that square root of mu is positive. Sorry, it's stable, and negative square of mu, it is unstable. Okay, it is unstable. And then when mu is 0, okay, when mu is 0, there is only one equilibrium. Which is a 0, 0. You can also do phase line analysis, phase portrait analysis. This is how the phase portrait looks like. But the thing is, when mu become negative, okay, when mu become negative, did you notice that there won't be any equilibrium? For example, -1 minus x squared. There won't be any x that make this guy equal to 0. And the phase portrait will look like this. Okay, that's how the phase portrait look like. Because x prime is always going to be negative. Okay, x prime is always going to be negative, so it's always moving to the left side. Always moving to the left side. The y prime up here will be pointing downward. Y prime down here will be positive, so the face portrait will be pointing upward. So that's why we call this problem is the prototype for saddle node bifurcation, because as mu crosses 0, depending on which way you look, you can say the equilibrium is being destroyed. Okay, if you going from positive to negative direction, there were two equilibriums, now becomes there is none. Okay, becomes none. So that's why we call this what a saddle node bifurcation. So now I will use a more complicated example to show how a saddle node bifurcation can occur. Okay, so this is just a very simple prototype problem. Looks very simple. It shows you how in two-dimensional system equilibrium can also be destroyed. So this simple example here, okay, it takes some effort to analyze, and there are some details that you guys may need to iron out by yourself. So this is the model that models the protein level and mRNA level in a cell. X is the amount of protein. Y is mRNA. You guys can look into the details how this works. But this is the system we're gonna be looking at. So as usual, we're gonna try to figure out equilibriums. So basically, I need to set the right side equal to 0. So I need y equal to ax. And I also need y to be x squared over b times by this. So basically, we have a straight line. We have another curve. When both equations are satisfied, we're going to be looking at our equilibrium. In other words, we need to look for intersections between the straight line and this guy. So we're going to set them equal, right? So when ax equal to this one, it'll give us the equilibrium. So obviously, doesn't matter what your a is, doesn't matter what your b is. Obviously, b here is not going to be 0, okay? A and b are both non-zero constants. This is always one equilibrium, okay? When x star is 0, when x star is 0, when x is 0, you plug that in, you get y. It's always 0. So this is always an equilibrium. When x is not 0, when x is not 0, from this equation here, okay, from this equation, you're going to cancel out the x here. You're going to multiply this across. Then you're going to be looking at this quadratic equation here. So figure this out. And when you expand this and apply quadratic formula, then you have the equilibrium given by this formula. Sorry, 1 minus 4a squared b squared. So algebraically, these are the additional equilibriums. Obviously, whether this exists or not, depending on this discriminant here. All right. So if 2ab is less than 1, if 2ab is less than 1, this discriminant is positive, then there will be 2 additional equilibrium. But if 2ab is bigger than 1, there won't be any additional equilibrium other than just 0, 0. No more equilibriums, okay? So if you look at this system here, obviously the critical number is when AB equal to 1/2. When AB equal to 1/2. If this product crosses this threshold, the additional equilibriums will be destroyed, okay? So that's why we call this what? Saddle node bifurcation. Saddle node bifurcation. Let's take a closer look at the graph here. So this is algebraic solution. We can actually solve this system and to find out the formula for equilibriums. I can also look at the graph, okay? Graphically, here's what happened. So we're going to be looking at the graph of a straight line ax and x squared over b times 1 plus x squared. All right. Or actually, I can multiply this across. I'll be looking at the graph of abx equal to x squared over this, because this curve will be fixed. All right. So this curve will be fixed. Teaching. So this is the graph of x squared over 1 plus x squared. As you can tell, when x is 0, it is 0. When x approaches infinity, it approaches 1. Okay, it approaches 1. So this became almost flat. So on the left side here, we have abx. That's always a straight line. So here is when ab is bigger than 1/2. There is only one intersection at 0, 0. And then there is this critical case when AB equal to 1/2. So there is one additional equilibrium. Now that is when this discriminant equal to 0, and that number is given by 1 over 2AB. 1 over 2AB. That's the only additional equilibrium here. And the third scenario is when AB is bigger. So when AB is less than 1/2. Okay, so this case is when AB is less than 1/2. So there will be 2 more additional equilibrium comes out. Okay, so that's the third scenario. So once again, when the parameter AB, okay, the product crosses 1/2, the number of equilibrium has gone from 1 to 3. So there will be 2 additional equilibrium pops up. All right, that's why we call this what? Saddle node bifurcation. Saddle node bifurcation. All right. And now I like to complete the stability analysis. I want to study the stability type for equilibrium, for the origin, along with those two guys. Okay, I like to do some detailed analysis. But otherwise, that's a quick bifurcation analysis showing this will be a saddle node bifurcation. Okay, saddle node bifurcation. To study the details of stability. To study the details of stability, we look at the Jacobian matrix. Jacobian matrix. Differential with respect to x, differential with respect to y, differential with respect to x. So you're going to do the quotient rule here. You get something like this. Differential with respect to y, you take negative b. So that's the Jacobian matrix. So there are different ways. I can just directly analyze the eigenvalues, or I can use the trace determinant graph. So the trace here is always negative a minus b. If you look up the trace um, determinant map that we showed you a while back, look that up, okay? If you look at the graph here, the trace is always negative. So the equilibriums are either sink or saddle. Here's that trace determinant plane that we talked about. If you look back to that trace determinant plane, whenever t is negative, okay, whenever t is negative, in other words, on the left side here, the equilibrium is either a saddle or a sink. It could be a spiral sink, could be a nodal sink, but it'll be a sink. Okay, it'll be a sink. So you can look that up. And the specific type depend on the determinant. So you go ahead, write down determinant here. So this part requires you to recall what we learned before and look that up, okay? At the origin, d will be, well, x will be 0, right? So d will be just ab. That'll be positive. So the origin is stable node or sink, okay? Stable sink. It's a sink or stable node. By the way, the A and B here, because we're talking about the real world model here, so A and B are both positive parameters here, both positive parameters. At the non-zero equilibrium, that refers to either one of those guys, okay, either one of those guys. D will be um, so up here is x star squared, okay, x star squared, and then the whole thing squared, x star squared, the whole thing squared. And we did a little trick here. We factor out AB. There's a 1 here, and we have minus 2 over 1 plus x star squared here. So there's a little trick that I did here, because if you go back to the way that we find out equilibrium, if you go back to that equation, that actually implies that AB is always the same as x star over 1 plus x star squared. Cancel out the x here, you got x star on the top and 1 plus x star squared on the bottom here. So AB is actually identical to this. So that's why this x star over 1 plus x star squared, that's really the same as AB. Okay, that's really the same as AB. That's why we factor that out, and what's left behind is 2 here and the one additional 1 plus x star squared. So this takes some thinking here, okay? So think about that, all right? Think about that. But that's the determinant at x star. So the rest is some detailed analysis, okay? Whether this guy is positive or negative. So let me talk about this. So here we basically have the one in the middle and the one that's bigger. Okay, this is the smaller one and that's the bigger one. So it turns out D is negative for the equilibrium in the middle. Because actually you can verify that at that point x star is less than 1. Okay, x star at that point at the middle equilibrium is less than 1. D is negative there, so it's a saddle. So once again, I need you guys to look up the trace determinant form and understand this. D is greater than 0 for x star that's greater than 1, okay? And also D that's less than AB. And also t squared minus 4D, you have to calculate the sign for this. 4D. Because D will be less than AB. If you look at this guy here, okay? From this formula here, when x star is bigger than 1, when x star is bigger than 1, D will be less than AB. D will be less than AB. So this is bigger than, D is less than AB, so this is bigger than 4AB. Which is actually just A minus B squared, okay? That's why this guy is always positive. Okay? Since it's a nodal sink. So I'm pretty sure you guys can do this linearized stability analysis. You don't have to do the way that we did it, but you can easily figure out the eigenvalues. Okay, you can easily figure out the eigenvalues. So what happened in the phase portrait for this problem we talked about is the origin is always stable. There is this one middle equilibrium that's actually saddle, and this one, the larger one, is actually nodal sink. Okay, this is a nodal sink. And the actual phase portrait can look like this. Zero, zero is always stable. Those regions all attracted to the origin. This is a saddle. There is a unstable part that connects this one with the nodal sink. There's another direction that goes in. So over here, okay, basically on this side, all the trajectories will move in this nodal sink. But this guy is a saddle, okay, this guy is a saddle. Alright, this guy is a saddle. So this is the case, this is the phase portrait when we actually have three equilibriums. But in terms of bifurcation, as we said, this is a saddle node bifurcation. Saddle node bifurcation. So that, once again, that takes some detailed study. Okay, takes some detailed study. And now I'm going to show you examples of transcritical and pitchfork bifurcation. Transcritical, that's where stability exchange. Pitchfork, that's when additional equilibriums popped up. And I will give you the prototype problems. Obviously, we can't analyze each individual one. I will present just one problem here, okay? You see how this is tied to the one-dimensional problem? You see the y prime is given by the simple equation. This is similar to the one-dimensional problem, okay? There is really no y in there. So this one turns out to be a transcritical bifurcation. This is a supercritical pitchfork. In other words, these are similar type of bifurcation with one-dimensional system, with one-dimensional equation here. Okay. So this is a subcritical pitchfork in 2 dimension. Supercritical, okay, supercritical refers to two additional stable equilibrium will be created. Okay, will be created. So we won't be able to do all three. So I will illustrate this. Okay, I will explain why this two-dimensional system undergoes supercritical pitchfork. And the way we're going to do this, once again, is plot the phase portrait. Plot different phase portraits when you change the parameter mu here. Okay. Supercritical pitchfork. For different mu values. For example, when mu is negative, when mu is 0, and when mu is positive. XY. When mu is negative, okay, when mu is negative, you will be able to find out that there is only one equilibrium that's at the origin, and the phase portrait looks like this. So you can think about why. Okay, you can think about why. It's very easy to see, but the origin will be stable in this case. Mu equal to 0 looks almost the same. Probably just the phase portrait is a little bit flatter. Okay, down around the origin, a little bit flatter around the origin. Finally, when mu is some positive number, so you can easily tell there will be two additional equilibriums. Negative square mu, positive square mu. Here's how the phase portrait looks like. The origin becomes unstable. Positive square mu, it's stable. This is how the phase portrait looks like. Negative square mu, it is actually also stable. So you can either use the phase portrait, or you can also do the linearization here. Okay, you can also do the linearization here. So when you study the phase portrait here, you claim this is a supercritical by pitchfork because the origin, it was stable, but then it lost its stability. Okay, lost stability. Along with the creation of two stable equilibriums. Okay, that's why we call this supercritical bifurcation. So obviously, in practice, you're not going to see the exact same type of prototype problem. Instead, you may look at a very different model, but apply the same idea to show that what kind of bifurcation are we looking at. So here it's no longer being the super simple model. Instead, it's a more realistic one. Show that there will be a supercritical pitchfork bifurcation at the origin in this system here, where mu again is being the bifurcation parameter. So you notice that this is very different from the very simple prototype problem, but the behavior is very similar. So we look at this one here to figure out the equilibrium. The x value and y value always have to be the same, and also 0. Okay, 0 is obviously one equilibrium. So let's take a look, because it's already indicating that there is a bifurcation occurs at the origin. So let's take a look at the take a look at the equilibrium and see what happened to the equilibrium at the origin. Okay. And hopefully we can guess a bifurcation value and then kind of confirm it. So this is true for all mu. The Jacobian at the origin is, so you guys go ahead and do this, okay? Jacobian differential with respect to x, you get mu and then plus cosine x, but then x will be 0 here, so that's why it's a plus 1 here. So we're calculating Jacobian at the origin. Differential with respect to y, you get 1. Down here is 1, negative 1. So I'm going to use the trace determinant thing here, okay, and kind of compare it. Trace is mu. Determinant so look up the trace determinant diagram, okay? You can easily see that the equilibrium, sorry, the origin is a stable node if mu is less than negative 2. Because in that case, the t here will be negative, t will be negative, and d will be positive. Okay, d will be positive. It is a saddle if mu is bigger than negative 2. So that suggests a pitchfork bifurcation. This suggests a pitchfork bifurcation at mu equal to negative 2. So that's our guess, okay? Because that's where the stability changes, okay? That's our guess. We need to confirm this, okay? We need to confirm that this is indeed a pitchfork bifurcation. In other words, there should be two symmetric equilibrium. So to confirm this, symmetric pair, okay? Close to the origin. The reason is because I can't really solve this by hand because you got a sine x in there. All right, so I can only kind of approximate this and confirm this. Okay, confirm this. That's why we say seek a symmetric pair of equilibrium close to the origin. For mu that is close to -2. Because at -2, there's probably just one equilibrium. So that means I have to solve this problem here. Solve this equation here. We need to solve. You see here, y will be the same as x. Plug that in. So I need mu x plus sine x equal to 0. So notice I can't really solve this by hand. So I have to approximate this when x is close to what? Close to 0. This is just mu plus 1x. It's a linear term. And sine x, as we know, can be expanded by Maclaurin series. And plus some higher order term of x to the power 5, okay, equal to 0. So this mu plus 1 plus another one, a minus x squared over 6, that will be approximately equal to 0. So approximation, okay. So when you solve for x star, it's approximately around this one. So that's the approximation for the equilibrium when mu is bigger than -2. When mu is less than -2, this will be negative. Crosses -2. So we don't really have the exact formula. I'm not saying this is the exact formula, but we're saying based on this preliminary analysis, it appears there will be a pair of equilibrium occurs, and the zero equilibrium lost the stability, and the pair of actually it's a stable equilibrium, okay, that we didn't really analyze it. Stable equilibrium occurs. So this is a pitchfork bifurcation. Zero lost stability. I guess those two pairs, okay, actually become stable. Those two pair, that pair of equilibrium becomes stable. So that's why we call this supercritical pitchfork. So based on these examples that I showed you guys, so this part is very much similar to a one-dimensional problem. They share similar behaviors in terms of the creation of new equilibriums, and they change stability. So these are pretty close. Our last topic will be a very important part. It's probably the most important part for dynamical system, is a different type of a bifurcation that we call Andronov-Hopf bifurcation, or sometimes simply Hopf bifurcation. And I will record a different video for this. Okay, so that'll be our last topic, which is Hopf bifurcation.